Minimize that. The next one, we're just going to do it twice because they gave us the second derivative. Oops, too far. Can't get my scroll bar because they got that thing in front of it. All right, I'm going to try just writing on here. Bingo. I do actually have a laptop. I should have it powered up and ready to go, huh? So, what is the integral of g double prime going to be? It's going to give you g prime.
Yeah.
And then you're going to integrate it again to get g. Okay? So, this is equal to the integral of 2. Let's write it this way because it's easier to integrate when we have exponents and everything in the numerator. So what's the integral of that?
It would be, it's -2 for the exponent. Yeah, it's -2.
Okay.
And so now
you
divide them.
In other words, you always, yes, you start with the exponent. That's the only thing I'm starting with. It's the only thing I'm doing. It's adding 1 to the exponent, and now I'm dividing by the new exponent. It's real simple. It's a two-step process. Add 1 to the exponent, divide by the new exponent. Okay? So that's equal to minus t to the minus 2 plus c. Now, they give us this initial condition, which is g prime, here's g prime, of -1 is equal to 1. So how do I solve for c based on that?
You just plug.
Give me the whole thing. In other words, first of all, that's out of there now. And here's what I've got. Let me write it so you can read it instead of on top of everything else. So here's what I've got. The integral of g double prime was g prime.
Yeah.
That's a typo. That should be a t. It's not x. It's a function of
yeah.
Okay? So, if that is true, and they tell us that g prime of -1 equals 1, that's what that says, is that's equal to 1. So solve this for c.
So you just plug -1 in for -t.
Not for -t, for t.
Or for t, and so you get negative and -1 raised to -2 plus c
Equals what?
equals 1.
Right, okay. Now that allows us to solve for c. What's that equal to?
One over square root of 1. So it would be 1 over 1, which is 1.
No, hang on, let me do it step by step. This is 1 over, there's the first negative sign. There's the second negative sign, but it's in parentheses and it's squared. So that's what I'm doing. Now do the bottom first.
Oh. So it would be negative 1 over 1, so it's negative 1.
Okay, so we get 1 equals negative 1 plus c. C equals 2.
Okay.
Okay, so C equals 2. That's what G prime of T is, right there. Let me go over here. Start doing the math here. So G prime of T equals minus T to the minus 2 plus 2. Now we're still looking for G of T. So what am I going to do?
You're going to take the integral of it.
I'm going to take the integral of that, and then when I take the integral of the right side, I'm going to split it up and do it like this. Okay? That gives me G of T on the left to give me on the right.
It's negative 1 for the exponent.
Okay.
And then it would just be T to the negative 1 because you would divide it by negative 1.
You don't have to explain it if you get it right. What's the integral of 2?
2t.
And what else do I need?
C.
Okay. Now they give us this identity. That initial value is what it's called. And whenever you see an initial value problem, it means that you're going to integrate, you're going to have a C, and then you're going to solve for that C using the initial value. Well, they're telling me G of 1 is equal to 1, so what can I do?
Plug 1 in for the t's and then set it equal to 1.
Okay, so when I plug in 1 there, I get 1. Plug in 1 there, I get 2 plus C. What's C equal to?
Negative 2.
And my equation is, and this is the final answer, and they'll probably want you to put your answer back in the way they kind of gave it to you. That should be what we find. 1 over t plus 2t minus 2 for 4b. No, they gave it to you with a negative exponent. We got the right answer, but just the way they presented it. I actually prefer this way. The answer they give you, I prefer, if I was a teacher. Because why have people put that back to a positive exponent? Calculus is all about the exponents. So you want, if something's going to be in the denominator, a variable, you'd rather always have it in the numerator with a negative exponent. Takes away a necessary step that you would have to do. All right, these fairly straightforward. We can go through these quickly. Give me the first one.
So it'd be
again, always start with that exponent.
Yeah, it'd be squared. And then so you divide it, so it's x squared.
Well, here's what it is.
Plus, yeah, and then plus cosine x. Yeah.
Almost. I don't know.
Cosine x.
I don't know how strict your teacher's going to be if you leave off these C's. Maybe really strict. They may just take 1 point. They may take off everything if you don't put that plus C there.
Yeah.
Especially given the problem we just did before this, where you had to put that plus C in there as part of the problem. Couldn't solve it otherwise. Whoops. Okay, about number 6. Ooh, this is a little harder. Not really. Go ahead. What's your first step going to be on 6? Do you have a product rule for integral?
I don't think so.
No, you don't. You're absolutely right. You don't. You kind of do, but you probably haven't learned it yet. That's what integration by parts is. Integration by parts is the equivalent of the product rule. It's just a lot more difficult. So, if you haven't had that yet, then the only thing you can really do here, now you must have had integration by substitution also.
Yeah, that's what we just started. Okay. And that stuff I
can help
couldn't
a lot.
Really tell you.
Integration by substitution is very understandable. You just have to approach it a certain way. But that's not what we're going to use here. That wouldn't actually help here on number 6. What can I do on number 6 to turn it into a simple integration problem? Distribute that v to the 2
thirds. Yeah.
Times v is v to the 5/3.
So it would be v to the 5/3 minus.
Hold on. Always start with your exponent and add 1.
Oh, yeah, so your computer just or either my internet just lagged, so I didn't see where you just
see what I was writing. Okay.
Yeah, so that's why. Yeah, I'm good. It just lagged a little bit.
V to the 5/3. And don't try to do it all in one step. Do it in 2 steps.
It'd be 8/3.
Divided by what?
8/3.
Right. Or multiplied by 3/8. Now that step I don't mind you doing all at once. Whenever you're going to divide by a fraction, go ahead and multiply by its reciprocal. You'll save yourself a step. Okay, what about this part here?
It would be 5/3, so it would be then 3/5.
Perfect. Here's your answer. Now, I know you know how to do 7, correct? What's the integral of 2?
2p.
Okay. The rest of it I know. You know how to do it all, correct? You know how to evaluate it from 0 to 2? All right, let's go. Yeah. I know you know how to do 8. You might not know how to do that part. Let's just talk about that for a second. What's the integral of that?
That would just be sine t.
Sine of 2t.
Yeah, sine 2t.
Right. We have to divide that by the derivative of the inside. The inside in this case is that. So you got to divide it by 2. And those 2's do not cancel one another. One is part of an argument of t, and the other, or the argument of the sine function, and the other is just a 2. Okay? So that's how you take integrals when it's sine or cosine and there's a coefficient in front of the variable. You just divide by that coefficient. In other words, the integral of sine of 3t is negative cosine. This never changes, but I got to divide it by 3.
Okay.
Okay? Now, let's just, since we have talked about it, talk about 9. Ooh, we only got a couple minutes. You want to do 9? It might take 5 minutes.
Yeah, let's just do it.
Okay, good. Because you got 5 minutes coming up, at least, since I had to reboot my computer. When you use substitution, here's what you're looking for. Pattern recognition. You are looking for a composite function multiplied by the derivative of the inside of that composite function. Okay? For example, if I had, and I'm not sure this is such a great example, but I guess we'll just use it. Okay? That's a composite function right there. The inside of that composite function is that part right there. What is the derivative of that part?
It'd be
Derivative, remember, not the...
3x squared minus 3.
Aha. And then I can factor a 3 out, leaving x squared minus 1. Ah, that matches that. So that is exactly what we're looking at. Now I've got this extra 3, but you can always take constants out of the integral. Okay? So here's what I'm really looking at here. I am looking at the integral of x squared minus 1, and then I'm going to integrate that just using the product rule. Which means I'm going to add 1 to that and divide by 4. Now, why does this work? And there's a 3. I'm going to take that 3 and put it out there. Okay? This works because if I told you to take the derivative of that, what would you do? You would apply the chain rule, correct?
Yeah.
In other words, you would 4 times that to the 3rd power times the derivative of the inside. The derivative of the inside is right there. I could tell it when I first looked at it because I'm trained in looking for this pattern recognition. And that is the key thing for using U substitution. Now, let me explain it just a little bit better. If I'm going to use U substitution, that's U. Okay? In other words,
Yeah.
U is the inside of your composite function. Well, what does that make du dx?
Wouldn't it just make it 3x squared minus 3?
Okay, which makes du be 3 times x squared minus 1 dx. See how I got from there to there?
Yeah.
You can treat differentials like fractions, basically. I can multiply both sides by dx. Okay? Now, that makes dx equal to du all divided by 3 x squared minus 1. So what my goal is to take that integral that is an integral in x and convert it to an integral in u. And the beauty of that, you'll see it in a moment. I've got to substitute every single thing here, okay? Well, I'm going to leave that x squared minus 1 there for a moment. But I've still got this. And what is dx? Dx is that, right?
Yeah.
So I'm going to substitute for dx. That dx right there, I got to substitute for it. If I'm going to turn this into an integral in u, then I got to get rid of all my x's. Well, what is dx? Dx is du all over 3 times x squared minus 1. Now notice what happens. All of the x's disappear. These x's cancel. This is actually u, so I have an integral of u to the third over 3 du. So I've turned that entire integral that was in x into an integral in u that is very easy to do. What's the integral of this u?
It would just be x to the third minus
Hold on.
3x to
Do
the
it
third.
in u. It's not an integral in x anymore. It's an integral in u.
So it'd be u cubed minus
Okay, always start with
3u.
the exponent. Always start with the exponent.
Oh, wait.
Start anywhere else.
So the integral is,
Add
so
1.
it's, yeah, 4,
Divide
and
by
then
the next
divide by that.
exponent. In other words, the new exponent's 4, so I'm dividing by 4, which is 4 times 4, 12.
Okay.
Okay, so that is my integral. Now I just have to go back because I used u to solve it. I now have to go back and resubstitute. So if this is my answer, oh, what was u? U was that. So I've now got x cubed minus 3x to the fourth divided by 12 plus c. That's the answer you're going to see in the book or the bottom, and that's the way you do it. Is you take an integral that's in x and you turn it into an integral in u. And u is always the inside of the composite function. That is the u. And how do I know that this lends itself to u substitution? Because it's being multiplied by basically the derivative of that inside. Not quite, because the derivative is 3x squared minus 3, but this is the important part right there. That 3 is a constant. I can always get rid of it, or I can always handle it. It's the x squared minus 1 that has to cancel. If this came out to be x squared minus 2, wouldn't work. Would not be able to use u substitution for this. U substitution is a very, very narrow range of problems that can be used for it. And there's only 2 cases. One is called this case, pattern recognition, and the other is called change of variable, which we don't really have time to go over today, but we'll cover that next time if you want, as well as the rest of these. Okay, but this u substitution, you need to do a bunch of them, practice them, repeat your method over and over and over, and eventually you get it. You do, you really get it. And I can help further with it because there's a couple of ways to do all of this. Don't have to do every step of that. There's some shortcuts you can take. But if you really want to understand the process, understand every step of that step over there. And also know this, that when you do integration, almost always the first step is differentiation.
Okay.
You use an equal amount of differentiation as you do integration, doing integration. There's very few that you can just do in one step. We didn't use differentiation there. But anytime you get into u substitution or any integration by parts or partial fractions, the first step is always differentiation. Okay? So, Mitch, I will let you go. Sorry for the technical difficulties and taking you over, but I'm sorry I didn't attack this U substitution before the others, but just because I can definitely help you a lot with U substitution. Okay?
All right.
All right. I'll talk to you next time, Mitch.
All right. Thank you.
You're welcome. Bye-bye.
Bye.